Hi, everyone. Now we're going to connect what we just learned about orthogonal sets of vectors and orthonormal sets of vectors to other parts of linear algebra that we feel more comfortable with, in particular, matrices. So we'll talk about orthogonal matrices next, and then linear transformations a little bit later on. Now, the columns of an m by n matrix Q will form an orthonormal set if and only if you take Q transpose times Q, you get the identity matrix. At least the n by n identity matrix. Now, why is that true is not hard to see. Because the columns of Q, Q1, Q2, so on, if they're orthonormal, that means if you take their dot product, that dot product is going to be 0 if the indices are different columns. Or it'll be 1 if the indices are the same column. But notice that Q transpose times Q has to be an n by n matrix because M is a m by n matrix. So then just by doing normal matrix multiplication, it must be an n by n matrix. But if you look at the ith jth entry of Q transpose times Q, so that would be the ith row of Q transpose multiplied to the jth column of Q. But the ith row of Q transpose is just the ith column of Q. So the ith row of Q transpose is just the ith column of Q. So then that ith jth entry has got to be Qi divided with Qj. But we know what that is. If I and j are different, that dot product is 0. If I and j are the same, that would then be 1. But that means then that off the main diagonal, where the row and the column indices are different, the dot product is 0. So off the main diagonal 0. But on the main diagonal, where the row and the column are the same, the dot product is 1. So on the main diagonal, the entry is 1. Off the main diagonal, the entry is 0. That's the identity matrix. That's why. Really easy. So because of this, an n by n, notice it's square matrix, a n by n matrix Q, whose columns form an orthonormal set, is called an orthogonal matrix. So by the previous theorem, instantly what you get is that Q transpose times Q is the identity matrix. But here, Q is an n by n matrix. Remember, that's important. The previous theorem didn't require that, but this here, you only call a matrix an orthogonal matrix if it's square. Well, but then also by pretty much instantly by the great Fallin-R equivalence theorem, the fundamental theorem of invertible matrices, one of the consequences I gave you of that theorem is that if the product of two matrices is the identity and they're both square, then they're both have inverses and they're inverses of each other. But to be inverses, you can change the order of the multiplication and it's still the identity. So that means then that Q inverse is actually Q transpose. So that's amazing. That means it's insanely easy to find an inverse of any orthogonal matrix. You just take its transpose. That's crazy great. Now there's other consequences that are also important, but let's first focus in on some matrices that are orthogonal matrices and others that are not. So first, you can tell usually really quickly if a matrix is not an orthogonal matrix. One quick way is just look at the columns. Take the dot products of different columns. If that dot product is not 0 anywhere between two different columns, or if the length of any column is not 1, well, then that can't be an orthogonal matrix. So if you look at this first matrix, just look at the very first column. Scary here. That guy's length is not 1. Because that vector, that first column's length is not 1. This cannot be an orthogonal matrix because the columns must be an orthonormal set. Look at the next one. If you look at these vectors, these lengths are all 1 this time. But if you take this vector and you take its dot product with that vector, that dot product is not 0. So therefore, this would not be an orthogonal matrix because the columns must form an orthonormal set. Now, there's another way too, if you want to check, but it's usually kind of just doing what I just said by cranking it out. By definition, a matrix is an orthogonal matrix if and only if that if you take the matrix transpose times the matrix, you get the identity matrix. So if you want to do the work, you can take this matrix, you can take its transpose and multiply by the exact same matrix again. And then just convince yourself by doing the multiplication that multiplication, in fact, is going to be the identity matrix. I won't do the computation. I'll just leave it for you to verify. So that's one way to do it. If you really think something is an orthogonal matrix, just take the matrix and multiply the transpose of that matrix to the matrix. See if you get the identity matrix. You can also, by the way, if it's orthogonal, it's invertible. So you can take the matrix times its transpose. That also has to be identity. So it's really easy to figure out if something is or is not an orthogonal matrix. You have these two techniques, one just by inspection and the other by doing the actual multiplication. Now, there are certain properties that orthogonal matrices have that are really interesting to know about if you think of it in terms of a linear transformation. So if you look at the linear transformation defined by this matrix, so the matrix Q is the standard matrix for this particular linear transformation, where Q is an orthogonal matrix. Orthogonal matrices have a couple other really neat properties. One is that if you take two vectors and you take their dot product, now take those two vectors and take Q of each of them. So multiply X and Y on the left-hand side by Q, and take those new vectors, QX and QY, and take their dot product. Those dot products are the same, always. Now that's important because if you remember, in order to find the angle between two things, you need their dot products. Now, to find an angle, all you need is their dot product and their lengths. Well, it just so happens, though, also with orthogonal matrices, that if you take the vector and take its length, and take Q times that vector and take its length, those are the same length. So the orthogonal matrix, if you think of it as a linear transformation, applying the transformation of the matrix multiplication to this vector, to every vector in the plane, orthogonal matrices never change lengths and never change dot products between vectors. Since they do both of those, they never change dot products and they never change the lengths. That means they don't change angles. So then an orthogonal matrix, if you have a linear transformation, that's a matrix transformation, that's defined by a orthogonal matrix, then that linear transformation never changes lengths of anything and never changes angles between anything ever. So then this is one of those really important, super useful things to know. Graphics, computer graphics is built on this statement right here, this very statement. So I'm going to explain why a little bit. I'm going to prove at least one of the equivalences. I'm going to prove to you that if Q is an orthogonal matrix, then the dot products will be the same before and after the mapping. So to do so, it's not hard to do. I'll just go through it quickly. Suppose Q is an orthogonal matrix, and Q transpose times Q is I. That's just one of the direct results from it. But that means that if you remember, if you ever take two column vectors, then that vector written as a, not as a column, but as a row, if you take that row times that column vector of Y, that normal matrix multiplication is actually the same as just their dot product. It's just X dotted with Y. This is important because I'm going to make that connection between dot products and matrix multiplication again. So if you take QX dotted with QY, but QX dotted with QY is the same mathematically, if you ignore the matrices, just think about the numbers, as QX transpose thought as a matrix times the matrix QY. But we know about transpose is that you can distribute the transpose through the matrix multiplication, just reverse their order and take their transpose. Q and X are both right now thought of as matrices. So you can get that. It'd be X transpose times Q transpose times Q times Y. But we know Q transpose times Q is I. So if you just put the identity matrix in between that product, it doesn't matter. The I goes away. And you just get X transpose times Y, which we know is X dotted with Y. So we then have that QX dotted with QY is the same as X dotted with Y. So the applying the matrix Q to these vectors does not actually change their dot product. Now we'll go the other way. Let's assume that their dot products don't change. So for any, no matter what you give me, any X and Y, their dot products don't change. Okay, I have to prove to you now that Q has to be an orthogonal matrix. To show you that Q is an orthogonal matrix, to show you that Q is an orthogonal matrix. What we'll do is this. I'm going to first figure out what the columns of Q are. I'm going to take their dot products. I'm going to convince you that that dot products is either 0 or 1. 0 if the indices are different, 1 if they're equal. So notice, though, that if you take the ith standard vector, so that's E1, E2, and multiply it on the left by Q, you have to get the columns of Q. So that's Q1, Q2, and so on. All right, now take two columns of Q, Qi and Qj, and take their dot product. Well, Qi dotted with Qj is the matrix Q times Ei dotted with the matrix Q multiplied to Ej. But I just said to you that whenever you have a dot product of two vectors where there's Q in front of them, the dot product doesn't change. So that dot product is the same as Ei dotted with Ej. And we know that Ei dotted with Ej is going to be 0 if I and j are different, and it's going to be 1 if they're equal. So therefore, Qi dotted with Qj is 0 if the indices are different, and they're 1 if their indices are the same. That's the definition for what we mean by an orthogonal matrix. And that's it. So that's a nice little result. Now, there's a whole lot of other results, but I'd like to give you a picture so you have an idea what we're talking about here. So you have a numerical example to work from. So if you remember rotation matrices, so if you're working in a plane, let's say you want to take the transformation that's going to rotate everything 30 degrees. So I'll go from R2 to R2. We know the standard matrix for that 30-degree rotation. That was going to be, it was the cosine of 30 degrees, sine of 30 degrees, it was negative sine of 30 degrees, and the cosine of 30 degrees. That matrix happens to be, it's the square root of 3 over 2, 1/2, negative 1/2, and square root of 3 over 2. Do you notice how that's an orthogonal matrix? It's actually an orthogonal matrix, right? Because the lengths of those columns are 1, and the dot product of the columns is 0. So then that's the columns form an orthonormal set of vectors. So therefore, it's an orthogonal matrix. So I actually know that that matrix has an inverse. Well, you guys think of it as the counter rotation. So there's the rotation and there's the counter rotation. But I'm more interested in seeing what the mapping does. So drawing a not so great picture. So here is space. And over here, we have some kind of triangle. Now, think about these vectors. This guy here and this guy here. When you rotate this picture 30 degrees, oh boy, I'll try to make it right. You rotate this picture 30 degrees, that's terrible. The vectors move here. Now, if when you rotate this 30 degrees, if it really is a rotation in your head, you think it's the same picture, right? It's the same picture. When you say it's the same picture, you mean that this length and this length are the same, which, because we're rotating vectors, they are the same length. You also think that this vector and this vector, their lengths are the same, which they have to be, because all we're doing is rotating the vectors, and we know that this mapping is an orthogonal matrix, and it preserves lengths. And the last one is that if we're really just rotating the picture, then this angle here and this angle here have to be the same, which it has to be, because we're the outside vectors, when you apply Q to them, when you apply this rotation matrix, since the rotation matrix is an orthogonal matrix, it preserves dot products and lengths, which means it has to preserve angles. So then this little result I just gave you about orthogonal matrices is the mathematical justification behind that when you rotate things, that you don't really change really the way they look, you just spin them. Neat, right? All right, that's good enough for that then. Now there's lots of other facts about orthogonal matrices that will connect the orthogonal matrix and therefore an orthonormal set of vectors to statements about the determinants, statements about eigenvalues, statement about the product of orthogonal matrices. So it winds up being that if you ever have any orthogonal matrix, its determinant is either 1 or -1. It has to be. So if the determinant of a matrix is not 1 or not -1, if it's something else like 2, it can't be an orthogonal matrix. If there's an eigenvalue, the absolute value, the magnitude of that eigenvalue has got to be 1. Has to be. So it's either 1 or -1, or it could be I or -I if we're using complex numbers. If a matrix is a orthogonal matrix, its transpose is also instantly orthogonal. Its inverse also is automatically orthogonal. These are just statements from just basic matrix multiplication. And if you have 2 orthogonal matrices and you multiply those together, the result actually is also an orthogonal matrix. So proving any of these is incredibly easy. They all boil down to remembering that Q transpose times Q is the identity matrix. So again, they're all very easy to prove. I'm going to just show you 1 or 2 of them. So let's look at the second and the third. I'll show you them. The only eigenvalue will be the eigenvalues whose magnitude is equal to 1. And I'll show you that Q transpose is actually also an orthogonal matrix. So I'll do it quickly. Let's suppose you have some eigenvector for this particular orthogonal matrix corresponding to lambda. Well, oh, and that should be the matrix Q. It should be the matrix Q right here. Q, not A, Q. So then the length of the vector X is equal to the length of Q times X, because we know orthogonal matrices preserve lengths. But Q times X is lambda times X because X was an eigenvector for the eigenvalue lambda. But then you have lambda times X in a length. So you can take the length, you can take the scalar lambda out of that length operation to get the absolute value or the magnitude of the eigenvalue times the length of X. Well, if the length of X is equal to the magnitude of the eigenvalue times the length of X, since X is an eigenvector, it's not the 0 vector. We can cancel on both sides, getting that the magnitude of the eigenvalue is 1. So it's either 1 or -1, or if it's in complex number, it's I or -I. So that's that proof, really easy. It's just a matter of using the stuff I just showed you. Doing it one more time, I'm going to show you that if Q is an orthogonal matrix, then Q transpose is an orthogonal matrix. Now just remember that if Q is an orthogonal matrix, that means then that Q transpose times Q is I. But it also means that Q is invertible. That means if you reverse the order, it's still I. So Q times Q transpose is also the identity matrix. I'm going to convince you that Q transpose is an orthogonal matrix. So by definition, I have to show you that Q transpose times Q transpose is the identity matrix, because that's the definition of orthogonality, that it's going to be a matrix is orthogonal really if and only if it's a square matrix, and Q transpose times Q is the identity matrix. So I'll now convince you that Q transpose has that property. So Q transpose times Q transpose times Q transpose is the same as Q times Q transpose, because Q transpose, that's this guy, is just Q. But I just told you though that Q was an orthogonal matrix. So then Q times Q transpose has got to be the identity matrix. So that's it. That's the proof. That shows you that Q transpose is an orthogonal matrix, because the matrix transpose times the matrix is the identity matrix. That's what it means for the matrix Q transpose to be an orthogonal matrix. Easy. And I believe that's enough for that video. And in fact, that's enough for this material. It's a lot of definitions and just messing with terms and connecting the ideas with what we already have in mathematics. Next lecture we talk about is we then attack the question of how do we actually project a vector upon a space? I've already told you the formula. I just have to convince you why it's true. And I have to convince you that there's only actually one answer. This is an incredibly useful result. It's just going to take us a little while to get to. So that's it for today.